Okay, so while we're getting our technical issues straight, it's a great pleasure to introduce Professor Ian Howat, who's going to be our keynote speaker today. Professor Howat got his bachelor's degree in geology from Hamilton College, and he got his PhD in earth science from the University of California, Santa Cruz. He is a professor in the School of Earth Sciences at The Ohio State University and is director of Ohio State's Bird, Polar, and Climate Research Center. He's spent over 20 years studying how glaciers and ice sheets form and respond to climate forcing on scales from minutes up to millennia and ranging in spatial scale from the formation of individual icebergs to continent-sized ice sheets on Greenland and Antarctica. He's an expert in airborne and satellite remote sensing. He has pioneered efforts to map rapid changes in the polar regions. He's been a participant and a leader in numerous scientific expeditions to Antarctica, Greenland, and Iceland, and he's the principal investigator of the Reference Elevation Model of Antarctica project, which is producing the first high-resolution terrain map of an entire continent. He received the Presidential Early Career Award in Science and Engineering, and he and his collaborators were awarded the Hyperion Innovation Award for their work on the Arctic Digital Elevation Model project in 2017. So when we talk about big data and huge amounts of data processing and data science, Ian is the kind of person who you may have in your wildest dreams of what might be possible. So let's see how we're doing on all of this. Yeah, I think yeah, that's right. I think we should copy it. I think otherwise we don't want this to just go scrambled in the middle. I hadn't realized when we invited Ian here that big data applied not only to his research but also to his PowerPoint presentations.
Oops, we need to enable the content. Yeah, sorry. All right. Here we go. Oh, it's backwards. Somehow missing the title slide, but that's okay.
Oh,
We'll go with it.
Strange. Okay, let's
that's
just go with it as it is. Yeah, if you go up here to slideshow. Oh, you okay? Oh, I see. Yeah,
Play
slideshow.
from start. How about that?
There we go.
All right.
Okay, so without further ado, Ian Howat.
All right. Great. Well, now that your expectations are sufficiently lowered, I'll begin. Yeah, if you were listening, I'm not really sure what Jonathan said, but if you're listening, I'm not really a data scientist. I'm clearly not a technical expert in anything here. I'll just talk. So I came to this kind of through the back door, literally. I came to this through the polls, and I'll show you why that happened. It's kind of this big mix of serendipity that allowed me to get into this whole crazy world of big data. Okay, is that working? Oh, now I have to lower my voice. That's going to be harder, actually. Okay. So it turns out that, of course, we use the Earth's surface a lot. It's where we live. It's our habitat. And since we've evolved these big brains and opposable thumbs, we build stuff, and we've now become a significant geomorphic agent on the Earth's surface, as these sample pictures show. And so the Earth's surface is a critical piece of, it's critical information, and we need to map it. We need to map it to do just about everything that we want to do, to build stuff, to locate stuff, to fight over things, to find resources. And so we invented this kind of science and engineering discipline called geoinformatics to tell us so that we could ask where things are, and not only where things are, but where things used to be, and what the state of those things were, and what the state of those things are now, and what we predict the state and location of those things to be in the future. And so I'm sure you're aware of the big data implications in this process because we live in a large Earth that's changing through time. And geoinformatics has always been, you could say it was one of the original big data projects. You know, starting 2,000 years ago, or more, 3,000 years ago, people started to want to trade with each other and go across the Earth. And so, of course, we had the Silk Road, which was the main thoroughfare between Asia and Europe for 2,000 years. And this was a big data collection effort. People would go to places, Marco Polo would go to China, and come back and tell everybody about what they saw. And so they collected data, brought it back to the centers of Europe. Of course, this data was sparse and not precise, right? But in the 1400s, I guess you could say, a data scientist named Fra Mauro compiled all this data. He wasn't the first. Ptolemy had done it, and others. But he was the first to make this giant map of the whole known world at that time. Okay, so this is the Mauro map. It's, I think, 10 feet by 10 feet or something like that. They didn't, you know, data visualization was a problem even then, right? So this was the Earth, the known Earth at this time. And you might look at that and say, well, what is that blob? That doesn't seem to represent the Earth very well. Actually, I think he did a pretty good job if we compare it to today. So you just got to, you know, flip it on its end. We're used to seeing north at the top. He had south at the top. But it actually renders better on my computer. Google it, and you can look at it. But he did a pretty good job considering they couldn't really measure longitude then. You know, I mean, this was all based on me telling you what I saw when I went on a trip somewhere. You know, it'd be like reconstructing a person's trip to Africa based on their summer vacation stories or pictures, right? So this map was accurate enough to launch the Age of Discovery. And the Age of Discovery was when, instead of people kind of randomly going out and doing trade and coming back and telling stories, people went out specifically to map the unknown. Okay? So this was a map done by another Italian, Toscanelli, who took the Mauro map and reprojected it, basically, and put it in a way that made it easy to chart what the Atlantic Ocean should look like based on that map. Now, he, of course, didn't know about North America. He also had his units wrong. And so that's why it looks like Japan and China are much closer to Spain. And so he did this, and he sent it off to Christopher Columbus, and the rest is history. And so, you know, we can say North America was discovered due to a unit conversion error. But that's how these things go. I think we all have made really good mistakes in the past. So the Age of Discovery, as I mentioned, was about taking little boats over long distances and mapping the Earth. And we realized that if you're going to take a boat over a long distance, you wanted to have actually a good idea of what was going to be there, and you didn't want to just trust the random person that said they saw a giant whirlpool surrounded by 4 islands at the North Pole. And so this launched the age of what you could say is precision in exploration, and actually mapping things you know are there. Okay, so this was one of the last examples of what we consider an old-style map, but by a very important person who came up with the Mercator projection, and something we still use today. And so these maps could be seen as enlightened maps, right? Instead of guessing about what you think is there, if you don't know it's there, you leave it blank, and you let somebody else find it. Okay, so we move through the Age of Discovery. We pick up the ability to measure longitude by ship. That became really important, and also elevation. And we wind up with the known world, you could say at the time when we still were bound by our feet and ships, right? We couldn't look at things from space or by air yet, but it's pretty impressive on how well the Earth was rendered at that time. Now, of course, we have this. We have the ability to see things from space and by air increasingly. And really, there's no problems now in finding the surface at a time you want. And, I mean, we can go to NASA now and look at the Earth yesterday. And we can look at it the day before that. We can look at it about every 12 hours in entirety. Of course, we still see clouds. But we live in this new age of being able to see close to everything, everywhere, all the time. I wanted to get my bearings around campus, so this is your typical Google Earth image of where we are. It was interesting to look back to 1992 and see what your campus looked like then. We were talking about parking earlier. A lot of your parking lots have been converted to buildings, so that's pretty cool. So yeah, we're in this silicon age of exploration. We explore the Earth as the Earth is rendered in layers and in points and vectors that are changing through time. And so we are building up this big data cube that's changing in time and space that we can explore. And of course, that's why this is a big data subject. And we're actually even growing these layers still. The capabilities we're adding to the vertical component of this stack, the different things we can sense from space, via radar, via the different sensors we have, and then the resolutions, and that's what I'm going to be talking about, is this new era of being able to see things that are the size of what you deal with every day, your car. Instead of the mountain range, you're actually looking at what the traffic conditions are right now. So I mentioned it before, but the silicon age is really everything, everywhere, and all the time. So everything are objects, points and vectors. Everything is their location, and all the time is how they're changing. And one of the things we're increasingly able to do now because of our observations is to look at very fine-scale processes. So I'm saying things that are happening at this scale of decimeters maybe, and measuring that over and over and over again over large areas and through time, and then being able to interpret how very large-scale processes are working. For example, I work on glaciers and ice sheets. I can look at how crevasses on individual glaciers cause icebergs to form, and then I can use that information then to build better models about how whole ice sheet margins are falling apart. Okay, and so that's really one of the new capabilities, freeing us from scale. Another big change in our new age of discovery, as opposed to those little boats going out into the ocean, is that we are no longer really data limited. We're right now software, so the algorithms we're building, and our computing infrastructure are the limitations right now. Now, you can think of this as a three-way race, and somebody's out in front and the other two are dragging behind, so it's constantly changing. Sometimes we're data limited, sometimes we're computing limited, sometimes we're software limited, but all of these things are equally important and have to be thought of in an equal way. And for kind of quirks I'll talk about in a minute, that's kind of the interesting part of this talk, the poles are where there's the most data. And this is why I'm standing here. Right? Like I said, I snuck into this whole thing through the back door, and I'll explain why in a minute. Oh, not sure what happened there. So I'm going to back up a little bit and talk about just one of these layers. Actually, my talk will focus really on one of these layers, the one that says digital elevation model. So this is what adds the third dimension into mapping, and increasingly the fourth dimension as well, as we look at terrain change through time. So this is kind of the revolution that's going on now, is being able to precisely map terrain at high resolution. So mapping the changing surface of the Earth at a scale that matters to you, something you can trip over. And we have three ways to do this. The first is stereophotogrammetry, so that's pictures. This is how drones are measuring three-dimensional shapes. We can use LiDAR, so lasers, and we can use SAR, synthetic aperture radar interferometry. So my talk will focus on terrain from space from stereophotogrammetry. This is the original remote sensing since the mid-19th century when the first photographs were taken. And it's amazing when photography was invented to the time when people were taking pictures from balloons was only about 40 years, to the time when people were strapping cameras to rockets and to pigeons was only shortly after that. And of course, to taking pictures out of airplanes was World War I. Right? So this is a rapidly evolved technology, but it's an old technology, and the principles of being able to measure things from photography was almost instantaneous after photography was developed. The original photographers were actually artists who were using it as a substitute or a better way to do art, and so they knew about perspective, and they knew that they knew what an image was built on and what it was representing. And it's really just a series of planes, of rays intersecting a plane, right? And so if we look at things from a different perspective, we can see things from different angles, and we have the ability in our brains to use the images in our eyes, our two eyes, to perceive depth, okay? And that's the same thing that we do with stereophotogrammetry and building terrain models, digital elevation models through stereophotogrammetry. We take two pictures, we look at how things move between the two pictures because we're looking at different angles, and then we can establish the height of those things above some reference surface. Okay, and this is a tremendously powerful thing because we can do this with just about any data as long as we know the geometry of the image, how high it was collected, the focal length of the camera, some of these details. And then we can, as long as we have good coherence between the images, we can see the objects in both the image, we can make an elevation model. And so we're doing this with current data, we're doing this with old data, we're doing this on the fly in your self-driving car. It's a pretty powerful thing, but it takes a lot of computing. Okay? And this has been one of the big evolutions over the past few years. So terrain from space really came, its big debut was with the Aster satellite, and that was launched in 1999. And this was the first satellite really dedicated to doing stereophotogrammetry from space. This is actually a satellite that it's still going amazingly. Talk about an engineering an underreport of lifetime on this thing. But it has two cameras, one looking down, one looking backwards. So it makes a DEM of every scene everything it flies over. And we're talking about scale of tens of meters. And this was used to make the first photogrammetric DEM of the world. And so this is a 30-meter DEM. That's really the stack of all data collected over a decade. So you can't really do change detection with this. Another limitation of this DEM, it's incredible, but another limitation for us glaciologists was if you look over the ice sheets, the data is not that good. And that's because the camera on this satellite doesn't do a good job discerning different textures over snow and ice. It just looks like flat white, so it can't build its elevation model. So a very powerful sensor, very useful in earth scientists, but not so much for a lot of us polar scientists. At the same time as Aster was launched, just about, IKONOS was launched. And this was the first commercial high-resolution imaging satellite. So at this time, it was realized, hey, we could put a satellite in space, take really high-resolution pictures, and sell it for a commercial interest to build, for building stuff, for planning, that kind of thing. And then, of course, the Department of Defense would buy some of the imagery to help supplement their reconnaissance. And so that was the business model, and commercial space-based imaging was born. IKONOS has led into other imagers that I'll talk about in a minute. But suddenly now we have the ability, you have to pay for it, but you have the ability to look at things at about a meter resolution on the surface. And these things can build DEMs. And you can build DEMs that have an accuracy in the meter range, but a spatial resolution of less than a meter. So suddenly you can start to measure the height of things that are about the size of a car on the surface just by shelling out some money. So IKONOS has led to multiple other satellites, both in the US and other countries, SPOT in France, and now Pleiades. In the U.S., we have Digital Globe with their Worldview constellation. There's actually, well, there was a Worldview 4. It's no longer operational. And these are continuing to get higher and higher resolution, so down to 32 centimeters from space. And these are pointing satellites. You have to tell it where to collect data, but you can get a good image of what you're interested in. At the same time, we're getting terrain information from radar. So in 2000, they decided to put a radar, a synthetic aperture radar, on the space shuttle. And so they basically put one radar on the space shuttle and then another radar on a big boom sticking out of the space shuttle. And using those two radars at the same time, you could do interferometry and get a DEM. And so this was the Shuttle Radar Topography Mission, or the SRTM DEM. Again, tens of meters resolution, but covered just about the whole world. Unfortunately to us polar scientists, it only went up to 60 north and down to 60 south. So sorry, Greenland and Antarctica and most of the polar regions, we still didn't have terrain. Now, present day, as of last September, you can now go online and freely get elevation models, not just in a mosaic, but also repeat elevation models down to 2 meters for the polar regions in both Antarctica and Greenland and the Arctic. These are the ArcticDEM and REMA projects that I'll talk about. So in the past, so over this period of time, in 20 years, the poles have gone from the poorest mapped regions of the planet, in fact, much worse maps than what we have for other planets like Mars, to the best mapped. And I think it's funny now when you look at the ArcticDEM mosaic map, the terra incognita is now the lower latitudes, and the poles are where we can see. And why is this? Well, let me also mention, too, that these are not static maps. So each one of those maps represents many, many overlaps of data. So we're starting to get at the time dimension, and I'll talk about that as well. So why did this happen now? Well, with a lot of things, and talking to people here, and the more I look at this, this becomes less and less unique. That you have the merging of 3 different capabilities, and that's the data. You have to have the software to analyze the data, and you have to have the computing power to process the data. And those 3 things have to come together to do what you want to do. And they came together to make these projects possible. So why the poles? Well, first we have to start with simple orbital dynamics. So these satellites, as in just about every imager, are polar orbiting satellites. So they have to be on the sunny side of the Earth to see, because they rely on sunlight, and they use the rotation of the Earth to push more land underneath their scan with each pass. So this should work. If this would run, what you would see would be an orbital pass over the surface of the Earth and lots and lots of coverage, over the poles and less coverage over lower latitudes. So because every pass it makes, you get a picture of the poles, and it takes lots of passes to fill in all of the mid-latitudes in between. So just by orbital dynamics, we have the most data at the poles. Okay, so we have the most collection capability at the poles. Why do we have all this data at the poles? Well, there's a lot of real estate in the polar regions. You might not think about Antarctica every day, but it's actually about the size of, bigger than the U.S. And we also have this Arctic region that has a lot of land around an ocean. And it's not of much interest except to scientists and, in the case of the Arctic, some resource extractors and things like that. So there isn't a huge amount of demand. And to the satellite imaging companies, this is kind of wasted capacity, right? When you're flying over the poles 1,000 times, it doesn't really matter. The only people it really matters to, or matter to at this point, were the people doing work every day in these areas, and these are the scientists, especially Antarctica. Okay, so in Antarctica, there's actually a tremendous amount of logistics that goes into doing science down there. You have to figure out where you're going to land planes. You're going to have to figure out how you're going to get your ship through the ice. And so up until the mid-2000s, this was very, very difficult to do. But through the hard work of the Polar Geospatial Center, based at the University of Minnesota, they were able to convince or work with the National Geospatial Intelligence Agency to start acquiring commercial imagery free of charge. Okay, so the National Geospatial Intelligence Agency had a licensing program, or have a licensing program, that allows federal agencies to get data for their operations, including their science. And so it seemed like an obvious thing to do would be to get this high-resolution imagery and help enable better logistics planning in the Antarctic and then after that, the Arctic. And so the Polar Geospatial Center started getting the data, using it for Arctic logistics. This is one of the first planned overflights and acquisitions of McMurdo Station in Antarctica. And the Polar Geospatial Center was so good that they were able to coordinate with the building folks down at NSF to paint the NSF logo on one of the oil tanks perfectly oriented to the orbit path. There was no reorientation of this image done. So now we can start to see our polar bases better than we can see, most of us can see, where we live every day. And so immediately these images were used for logistics planning, planning out ice-breaking routes for getting the icebreaker in to resupply the stations, doing maps of the stations, doing maps of field sites. Suddenly, if you're a geologist and you're going to some mountain in the Transantarctic Mountains that has only been visited twice in history and has barely any map, and you don't know where you're going to land your helicopter, now you can see it very clearly. You can know exactly which patch of snow you want to go and land on. If you're going out to the middle of the West Antarctic ice sheet to drill an ice core, you can get a very nice image of your camp, so you can start to plan where the flights are going to come in and where you're going to put your runways. And relatively quickly, because the PGC also happens to be very good and very committed group of people, they actually built a whole system for databasing this imagery. They thought way beyond logistics from the start. And they built their own viewer for viewing this imagery. So they have this continent now covered in sub-meter stereo satellite imagery, wondering what to do with it. So that's where the data came from. Now you need the software. So you go back 7 or 8 years, not even, and if you wanted to make a DEM, you would load up your software, something like ERDOS Imagine or something like that, and you'd load up your right image and you'd load up your left image, and you'd have to give the software some training to locate how those two images are matched up in space, and then there would be some algorithms that would then fill in the other, what we call tie points, that tie the images together. Of course, a labor-intensive process, and you're not going to do this with hundreds of thousands of individual DEMs. So over the past, since that time, multiple groups have been working on automating this process completely and without a sacrifice in quality. So can you completely automate DEM extraction with these satellites without losing any of the quality in the data? And so these are pictures of, on the left is Dave Sheen at the University of Washington, who helped develop the AIM stereo pipeline process for doing this. And then in my group, MJ and his family there, MJ No, who developed the SETSIM software that we use in the projects that we've done. But there's been this flurry of software development over the past 5 or 6 years by these really committed people who've put in a lot of work to develop and automate a system for the first time. And so now you can take your satellite imagery. If you have a left image and a right image, you just put in SETSIM image 1, image 2, and an output file name, and something like this pops out. This is Fairbanks, Alaska, a hillshade representation of Fairbanks, Alaska at 2 meters. You can see the airport, there's the river, lots of buildings. And so this is kind of the software workhorse that has enabled what we can do. So as of about April 2015, we had all this data coming in. We had built this software that can now take and analyze large amounts of data automatically. And we thought we were really doing a lot of good work by making this mosaic of the Western Greenland ice sheet margin. And I'm thinking of all the cool science we can do with this and how amazing it is. At the same time, the PGC is talking to the NSF about, maybe we could do DMs at a bigger scale. And this really caught on. And so I remember distinctly, I was actually in Maine on summer break, or right before going back to teach, and watching this on C-SPAN. Oh, if it's going to let me. Oh, but we lost audio.
And to help Alaskans better plan for sustainable development, the National Geospatial Intelligence Agency and the National Science Foundation are leading a public-private collaboration to create the first ever publicly available, high-resolution, satellite-based elevation map of Alaska by next year and the entire Arctic by the year after that, so that we know exactly what's taking place all across this great state.
Kind of hard to imagine, huh? But yeah, it's a little strange to see the president announce your project on TV. So so we thought, great, but we need a big computer. Well, thankfully, the University of Illinois has one. It's called the Blue Waters machine, and it works really nicely with our software. And suddenly, we have the ability now to produce hundreds of thousands of DMs per day. And we go from, measuring, can we do 100 square miles in a week or something like that? Now we can produce the equivalent of the lower 48 states in one day with this machine. Part of it is we've been very lucky to have a big chunk of that machine. This is a snapshot of allocation uses. I forget when, but at this point we were using over half, almost 70% of this very large supercomputer. So, with the software, with the data access, and with the machine, and also with the help of the President of the United States, we went from little part of Western Greenland in 2015 to the entire Arctic at 2 meters by 2018. And so this is Kotzebue, Alaska. That's where he gave his speech. President Obama gave his speech. This is the national elevation data set, so this is what you had to work with prior to ArcticDEM, and then this is ArcticDEM. And you can see the gym where he gave his speech is the biggest building there in the Kotzebue Peninsula. A crater in a volcano in the Aleutians prior to ArcticDEM, and now with ArcticDEM. So to give an example of where the elevation data set was actually relatively pretty good, but with ArcticDEM, we can see much more now. Anchorage, Alaska. And if we go to the airport, we can actually count the airplanes. And this is a place near and dear to my heart, Kangerlussuaq Airport, Greenland, where I've spent many weathered-in days waiting for the ice sheet to clear. And I mean, to see the Arctic, there's not many trees in the Arctic. So to a geologist, to be able to see the bedrock features in the Arctic at this resolution, to see the sculpting that the ice sheets have done on the Earth is just, it's an amazing source of wonder. Including Russia, and we can see the ice cap in Russia, in Nova Zemlya, Russia. And you see just kind of how vulnerable some of these communities are to climate change in the Arctic as well. This is Point Hope, Alaska, one of the most northern communities in Alaska. And you look at that and say, what is that out on that peninsula? But that's a community. And you can even see the berm that they've built, one to keep the sea out on one side and one to keep the snow from blowing off the lagoon on the other. So again, we have repeats with these data. These aren't a one-time thing. We're constantly taking more data. Every satellite pass, terabytes and terabytes are coming in all the time. And so as of September, this was the data density map. So this is the map of the number of repeats we have at a given location in the Arctic. And so we max out at 10 in this image. In some places we have hundreds now So we can look at changes through time, and that's really what the new frontier is here. So as ArcticDEM was starting up, I realized, we're spending all this time in production. We actually have to start figuring out what we can do with this data. At the time, there was a recent graduate, PhD graduate, Chun-Li Dai, who was looking for an interesting postdoc to do, and said, hey, I have 2-meter elevation models of both polar regions stacking through time, and I have no idea what to do with them. Why don't you take these and see what you can do? And so she has, and she's done a series of studies, and so I guess these will be a series of little lightning talks about what she's been able to do with ArcticDEM. And she has a solid Earth background, so she went right for volcanism and what we could see. And so with ArcticDEM now we can map out lava flows from volcanoes. And this is the Tolbachik eruption in the Kamchatka Peninsula in 2012. And we can see the volcano crater there and the series of lava flows coming off of the southern side of the volcano. And on the right, we have the time series of the elevation change at an area due to the lava flow. So the lava flow comes up, and you create this new terrace. And so she was able to measure that, map the volume of the lava flow, resolve new cinder cones being built by the lava flow. So the plot on the right there has individual cones that were created by the eruption. And she actually used this data to better refine the recurrence interval of eruptions from this volcano. She's also, in collaboration with some others at OSU, looking at rivers from space. So now that we have high-resolution topography, we have high-resolution river shorelines. And we can actually measure river height through time, first by locating the rivers using the imagery. So we map where the rivers are. And then we use high-resolution DEMs to map how the area of the river scales with the elevation of the river. So we're mapping the stream gauge basically from space. And so the plot on the right are measurements of a stream gauge on the Tanana River from space using ArcticDEM. Those are the points with bars, and then the blue is the actual river gauge. And what we found out is that, unlike the gauges, we can actually measure the river heights in the wintertime as well. And we can do this at a very useful resolution, and hopefully we'll be able to actually measure discharges from space. One very powerful thing once you start to look at lower latitudes is what we can see in terms of vegetation. Okay, so this is kind of just a random area in Siberia, and you can see the clear cuts and the effect on the surface. And we can actually use the repeat imagery then to measure how much deforestation is happening. So we look at a change in this image over 3 years in an area of Siberia, and you can see from the imagery at the top, the image on the left to the image on the right, we have several clear cuts that are made. This is the elevation map difference below, and so we can actually measure the 20-meter tall trees that are being chopped down. And not only that, we can see the access roads that were cut, and we can even see some stream bank erosion due to the loss of vegetation. So I do still find some time for glaciology using these data. So this is Helheim Glacier in Greenland. What you're looking at is an elevation change map over the glacier. The glacier is flowing in from the ice sheet to the left, flowing down into a fjord with icebergs on the right. Red means surface lowering, and that big patch of red at the front is where it retreated, right? So it drops to sea level. If we look at just one area in the triangle there and plot out that elevation change through time, that's what we have on the right. And so the blue dots, or the red dots, is the ArcticDEM elevation change at that point. You can kind of see it goes up and down with the downward trend. Prior to ArcticDEM, the only way we had to measure this glacier's surface elevation accurately was with LiDAR, and they'd fly a LiDAR every spring. And that's the blue dots. Okay? And so if you only had the blue dots, you'd say, oh, the glacier was stable and then had a big drop after the second survey there. But with ArcticDEM now, we can kind of fill in the time gaps and see that there's a seasonal component as well over a long-term trend. And that's one of the real big powerful aspects of this data set, is we can start filling in those time gaps where we only had accurate but infrequent aerial surveys before. Something that's really exciting that Chun-Li's done, that this actually just got published today, is a compilation of Coastline automatically extracted from the imagery for ArcticDEM. So we have stacks and stacks and stacks of repeat imagery over the coastlines. For worldview 2 and 3, this is multispectral imagery, so we can actually come up with a water index. And so by measuring the coastline over and over again with multispectral imagery, you can come up with statistics that tell you how likely a given pixel is water. Right? So we can come up with a water probability or a water recurrence interval map. And that's what we're looking at here. Is on the left, we're looking at a part of the coast of Alaska. The red is where it's very probably water all the time. The green is our inferred coastline based on that probability. If we take a little subset of that, that's what the little blue box is. So down below, we have the blue coastline over the image, where we don't think it's water's masked out, so you can see the background. The green, and they both look green, but the other two lines are the existing coastline, one from Goddard and one from the SRTM projects. So we can get a much better coastline. Our challenge, though, is at 2 meters, what is the coastline? You're within the tidal zone, right? You're within the zone of variability. So we have to redefine coastline. And when I asked the NGA what they want for a coastline at 2 meters, they weren't quite sure, because this is, you don't really have a coastline at 2 meters. You have a coastal zone of probability of there being water at any given time. So we're having to redefine what we're, and this is just illustrating that point. Same area on the left and the right are 2 different times, and that's just the land area change due to tides. So we're having to deal with redefining what we think about in terms of geospatial terms. Okay, so quickly I'll talk about REMA, which is the Antarctic version of the ArcticDEM, done slightly differently because Antarctica is really flat, right? So some of the things we worried about with ArcticDEM, we're not worrying as much about REMA. REMA, we're really trying to measure high precision change. So we registered things to altimetry a bit differently, but it's generally the same. So this is the first complete continent to be mapped, have its terrain mapped at this high resolution at under 100 meters. So just to compare, you know, a lot of people ask me, why would you bother mapping Antarctica at such a high resolution? Well, part of it's because we can. And I don't think we ever regretted having, you know, too much resolution. But really, what's incredible is the details and the things you see at high resolution that you weren't expecting to see. And when you have a flat surface like that, once you look at a hillshade at very high resolution, all kinds of things come out that were hidden before. So on the left here, we have BedMap 2. That was the old DEM, mostly based on satellite radar from the 90s. And then on the right, we have the REMA rendering. And you can see the huge difference in the surface texture that you can see. And I mean, we see things that I really can't explain, certain features in the surface. And just the details we get, this is the Mullet Glacier going from East Antarctica, draining into the Ross Ice Shelf. And then this in the bottom is Lake Vostok, is that big flat area. And over on the left here, you can see what looks like errors to be, at first. These are actually mega dunes, these waves in the surface. These are created by a feedback between ice flow and prevalent winds. And if we zoom in on Lake Vostok, you can actually see Lake Vostok, the base there, the Russian base. And that line out, that's the track left by the traverse that goes out to resupply Lake Vostok. So REMA, of course, has repeats as well. So we're looking at the time dimension. And in Antarctica, this kind of resolution at repeats through time, this is the first time we've ever been able to come close to doing anything with it. And we really haven't done much with it yet because it's so new. I do have a PhD student, Alison Chartrand, who's working on ice shelves and seeing what we can do with the REMA data set, looking at how ice shelves are changing. And she's specifically looking at these channels that form in the base of ice shelves. So what you're looking at is an ice shelf in the West Antarctic ice sheet. So the black is ocean, or there's some data gaps there. But this is ocean. The ice shelf is coming off the continent from right to left. And you can see those little channels in the surface, those kind of things that look like snakes in the surface of the ice shelf. Those are actually the surface expression of channels that are being eroded into the base of the ice shelf. So the ice shelf is being cut from underneath. And so because of freeboard, of just hydrostatic balance, the surface is lowering. And that's the surface expression you can see. And we know almost nothing about these things. We know they're formed by flowing meltwater freshwater cutting up the ice shelf from underneath, but we don't know how stable they are, or they mean the ice shelf is going to fall apart any minute. So with these data, we can actually start to measure these things through time. And so she's making maps of how these channels are changing and evolving for the first time. Okay, so what's next? Where do we go from here? I mean, just getting ready for this talk, it was really helpful because I really need to stop and take a reevaluation of how we got here so fast and help me figure out where we're going to go. But really, obviously, the thing is more data, more places. You know, this begins at the poles, but there's really little to stop it from going anywhere else. Of course, near real time, being able to use this data in a operational capacity to make decisions now is key. One of the things I haven't talked too much about, but another key point, is the power of multi-institutional partnerships and multi-sector partnerships. So partnerships between government, the private, and the public institutions are really important to get these projects going. And I think there's more interest among all parties to do that. We still don't really understand these data. There's still a lot of work to do in terms of the uncertainties of these data, the limitations of what we can resolve, what we can do. Vegetation is a big one, so ecologists out there that want to better use this data. It's not LiDAR. It's different than LiDAR. And so how do we synthesize this data with LiDAR to complement LiDAR? And then, of course, you know, I haven't shown any machine learning examples yet. All the algorithms we've done are basic algorithms that could be applied in a machine learning context, but it's wide open. I mean, this is an advertisement. Go online, get the data, and start playing, because this is probably one of the biggest, this is the biggest geospatial data set that's openly available. So when things are getting really scary, though, when you start to talk about small sats, and this is what keeps me up at night, is how do we deal with things like that? Okay? So these are drones in space. And there's more and more of them. This example is the planet Dove constellation. So I can show you the, it's going to let me do it. Here we go. So this was the launch of doves, of 100 and something doves in 2015, I think, from a launch based in India. So it gets, the vehicle gets into orbit, and then it starts dumping satellites. These things are amazing. Once they hit to the programmed altitude, they have gyroscopes that stabilize them, and then they go right into operational mode. So 104 in one go. How do we start dealing with this every few minutes? I don't really know. I mean, it's scary to think about, but the possibilities for data science are staggering. So when I think about this new era of Earth exploration that we're in, I'm realizing how much exploration is fundamentally changing. It used to be you had to predict something was out there, get in a boat, go see if it was there. You probably would die. But you know, that's how discoveries were made. Now, I mean, I can sit at my desk and I've got so much data I don't even know where to begin, right? So I need the computer to tell me how to discover now. And so how do we program software to enable us to discover in large data sets? That's really this new age of exploration we're in. And it's all, of course, about openness. This whole project wouldn't have happened if it wasn't essentially an open project. So open algorithms using government open to science computing to make freely open data. Okay, so that's critical. And then, as I mentioned before, we're in this era of constantly going between compute limited, data limited, and software limited. Right now, I think we're software limited, and so that's why I'm really glad to talk to you folks, because the opportunities for machine learning using this big pile of data and the powerful computing we have available to us is really important. So with that, I'll just leave this beautiful image of the Lena River Delta in Russia as part of the ArcticDEM project. Thank you.
So do we have any questions?
So, if I were the head of a three-letter agency in the US, or maybe its counterpart in some other part of the world, I'd be hiring Christo or someone like him to be obfuscating lots of features, because boy, are they visible.
Absolutely. Yeah. The only feature, machine learning feature detection project I know of using these data is being done by the Canadians right now. They have a few workshop papers out, but they've really just begun. I mean, this data has, the data type has existed now for 20 years. It's only in the past, really 1 year, that all of this big population of data has been openly available. So I don't think anybody was there was no kind of pre-building of algorithms in anticipation of this big data dump. So now that's why we're having to all catch up. But absolutely, the object extraction identification is critical.
How long before you're bouncing satellite signals off the moon or off of Mars and doing the same thing?
Oh, it's already been done. Yeah, Mars has a great DEM. Yeah.
Is that with satellite signals, or are you using the rover?
They have their own satellites, yeah. Mars does, yeah. In fact, we use our own in-house software. The other one that I mentioned, ASP, was actually originally developed for the Mars rovers for doing photogrammetry in space. And it was adapted to Earth satellite photogrammetry. Yeah, we're having to catch up with the planetary geologists.
A couple questions. How long before the whole Earth is done like this, and are there certain challenges that will make that impossible, like, you know, like government interference or that sort of thing?
Not government interference. The government is incredibly supportive of this project.
Well, what about other governments?
No, you know, we have to realize these are commercial imaging satellites, and this wouldn't be the only industry where there's issues with how you open up a traditionally commercial industry. And so I can't be more specific online than that, but the infrastructure is all there.
And then one more. What's the science that you are most excited about in terms of glaciers that will come out of this data set that you haven't done yet?
Yeah, all of the short time and space stuff space scale stuff that we haven't been able to resolve before. So water in and under glaciers, crevassing and iceberg formation, the stuff that happens it always happens when you're not looking, right? We'll be able to see those microprocesses that we then can scale up and make much better predictions about how the ice sheets are responding to climate change.
Recently in the news, there was an announcement that according to research, the glaciers are melting faster than was previously thought. So is this data somewhat responsible for these conclusions?
Yes, I do believe they used ArcticDEM data in that paper. Most of that paper, I think, most of the analysis was done before the last ArcticDEM release, though, so I'm not sure how much relied on ArcticDEM. But yes, one thing to realize, too, is the data has only really ramped up in terms of collection over the past 5 years or so. There's very little prior to 2012. So what's exciting, and getting to your question is, going as well, is going forward, now that we have these base maps. Because you need a reference map. You need a reference data set. We have that now. Going forward, every collect we get is a repeat. And it's a repeat of a repeat of a repeat. And so we are starting the time series. And when you think about something like Landsat, its value is that you can go back 40 years now and look at change. To be able to look at this time and space scale, decades into the future is going to be incredibly powerful.